G'day, Richard Marr from Mars Classes. This video we're going to have a look at electric fields. Now we've looked at gravitational fields in previous videos, but in this case we're going to be looking at not the impact that a field has on a mass, but the impact that another type of field will have on a charge. And when we're looking at these fields, we're going to have a look at a physicist who was really outstanding in his field, and that's James Clerk Maxwell. He recognised that once when he was traipsing around the Scottish Highlands and the clouds came down and he got lost and he pulled out his compass to find his way and lightning was flashing, whenever the lightning flashed, his magnetic compass needle would spin around. So he recognised that electricity and magnetism are related, and a lot of his work is what we are very thankful for, and without that you wouldn't be watching this on your mobile phone right now, because we wouldn't have signals that phones could send, or on your computer now. So anyway, the work he did is very different to, say, a farmer outstanding in his field, but by the same token, that farmer outstanding in his field is actually outstanding in the Earth's gravitational field. And if you recall an earlier video, we said that if you consider the Earth to be in space and it's curving the space-time around it and creating a gravitational field, if you place a mass within that gravitational field, it will experience a force toward the Earth. And the vector lines we've drawn there to represent the field, the arrowheads indicate the direction, and the density of the field lines will indicate the strength of the field. And we said that we could determine a value for the gravitational field intensity or gravitational field strength by looking at the force per unit mass. So the units of little g are going to be newtons per kilogram. But we also recognise that little g represents the acceleration due to gravity, so being an acceleration, its units could also be metres per second per second. So what's all this got to do with electric fields? Let's consider we have a negative charge, and near that negative charge we place a positive point charge. Now, by now you probably recognise that opposites attract, and in this instance that's exactly the case. The positive charge would be attracted towards the negative charge and would follow the field line down to the negative charge, so it will experience a force in the direction of the field. Positive charges experience force in directions of the field. But the same as the gravitational field, the density of the field lines will indicate the strength of the field. Now we can determine the electric field intensity by looking at the force per unit charge. So therefore the units of electric field intensity are newtons per coulomb. But just like the gravitational field strength had a couple of different units we could express it in, so too can the electric field intensity. As well as newtons per coulomb, we can also say that it is in volts per metre. Now how do we get that unit volts per metre from F on Q? To sort of help determine this, we'll have a look at a very simple circuit, electrical circuit with a source which is providing electrical potential energy, a battery, some conducting wires, and a load which is converting the electrical potential energy to some other form of energy. It might be motion or sound or heat or light. So the source of electrical potential energy provides energy to charges and pushes them around the circuit. Now, as they push them around the circuit, they'll be going in a constant rate. To determine the rate of the flow of those charges, we can stick an ammeter in the circuit. Now the ammeter measures current, and current is determined by the rate at which charge flows, or Q on T. And the units for current are amperes, and 1 ampere is 1 coulomb per second. So as that current keeps flowing around at the constant rate around the circuit, each of those charges have a certain amount of energy, and then they'll get to the load. When they get to the load, some of that energy will be converted to other energy and will no longer be electrical potential energy. So it'll give it out maybe as light or heat or sound or something like that. So each of the charges, as it moves through the circuit, will now have less energy. And as it goes through, you'll notice something that I think is really quite neat, is that the rate at which it flows is the same. The current will remain the same. The number of charges per unit time will be the same on either side of the load. But you notice I've stuck a voltmeter there either side of the load, because the voltmeter measures the change in electrical potential energy from one side of a load, or one part of a circuit, to another part of a circuit. So this particular voltmeter here is looking at the energy each charge has before it enters and comparing it to the energy each charge has as it leaves. So the energy per charge will be joules per coulomb, and that's what we define 1 volt to be. 1 volt is 1 joule per coulomb. Or to rewrite that as a formula, we'll say that the voltage is the work divided by the charge, or the energy divided by the charge. Now, With that information there, we can do a few little things. We can multiply the voltage times the current. And what would the voltage times the current tell us? If we multiply the voltage times the current, we'll get W on Q times Q on T, which will give us W on T. What is that? That's right, watt. That is watt. That is power. That is joule per second. So when we look at voltage times current, we get power. So that would tell us the power of the device, or how fast the energy is changing in the device. So we know a few equations. We know that the electric field intensity is force on charge. We know that the work done by an electric potential is voltage times charge. And we also know that in traditional way of looking at work, it's force times displacement. So those three equations we already know. So let's have a look at the two ones which we've got for work. We've got work equals V times Q and work equals force times displacement. Now they're equivalent. So let's get rid of the values for work, and we can say that V times Q equals F times D. And if we rearrange that, we get that V on D equals F on Q. Now if we look at the very top, E equals F on Q. So if the electric field intensity is F on Q, the electric field intensity also equals V on D. That's the equation we had earlier on when we said it was volts per metre. Now what does it mean? It might mean something like if you had two plates which had opposite charges, and between those two plates you were going to have a uniform electric field. To determine the electric field intensity in there, which is uniform, we would know there's a potential difference between the two plates, and there's a distance between the two plates, so we can use that to work out the electric field intensity. Okay, let's get back to the charges, in the central charges with point charges falling in towards them. Now this is the field we looked at previously where we had a negative charge and a positive point charge outside it. Let's imagine it wasn't a negative charge, imagine it was a positive charge. What's going to happen then? Well, then the field lines will be going in the opposite direction, won't they? But if they came close enough to each other, those field lines could join up and we're going to get a field like that. So you may have seen that type of shape of a field when we're looking at magnets. So when we start to look at magnetism later on, we'll see the relationship between magnetism and electric fields. Okay, that's with positive charges. Positive point charges in electric fields will experience a force in the direction of the field. If they're negative charges, imagine we change them to negative charges, what's going to happen? Now each of those charges is going to experience a force, but it'll be in the opposite direction to the field. So we've got that definitions of fields is that an electric field is a region of space which will influence a charge placed in it. The density of the field lines tells you the strength of the electric field. A positive point charge will experience a force in the direction of the field, and a negative point charge will experience a force in a direction opposite to the field. What we'll do in subsequent videos is have a look at some more of the calculations we can do with these equations which we're deriving and getting from this look at electric fields. So until next time, I will see you later.